Hi guys, we're going to continue on with VSEPR and electron domain geometry as well as molecular geometry. So today we talked about that there are two big factors that will determine molecular shape, and that's going to be the bonding electron pairs and the non-bonding electron pairs. So before we can even get to molecular geometry, I first have to know what the electron domain geometry is. So electron domain geometries can be one of these 5 big categories. So I could have an electron domain geometry in the linear classification. It could be under the trigonal planar. It could be a tetrahedral, a trigonal bipyramidal, or an octahedral. And then once we know these electron domain geometries, we can then predict its molecular geometry. So we said today that there are 2 types of electron domains. There's bonding and there's non-bonding. So remember that even if a bond is double bonded or if it's triple bonded, it still is going to count as one electron domain. So if I'm looking at this particular molecule, I have a domain here, here, and here. So I have 3 bonding domains plus a non-bonding domain. So I have a total of 4 electron domains, which would then make it a tetrahedral electron domain geometry. So this is where we left off with VSEPR, and valence shell electron pair repulsion theory is a theory, and right now it's the best explanation that we have, even though it's up for debate. So the best arrangement of a given number of electron domains is the one that will minimize the repulsion among them. So this VSEPR model is just based on the idea that electron domains are negatively charged, and therefore, because they're negatively charged, they're going to repel one another. So it's kind of like if you were to do these balloon arrangements here, the balloons are going to try to separate themselves as much as possible if I had 2 of them. So it's going to give me a linear orientation. If I had 3 balloons, then they're going to orient themselves so that they're trigonal planar, where there's 120 degrees between each of them. And then if I had 4 balloons, it would look more like this tetrahedral orientation. So it's just an analogy. So let's talk about the electron domain geometries. So I have number of electron domains. If there are 2 electron domains, then I consider that to be a linear electron domain geometry. If I have 3 electron domains, that's trigonal planar. If I have 4 electron domains, that's tetrahedral. 5 is trigonal bipyramidal, and 6 is octahedral. And all of the predicted bond angles are associated there on the side. So linear is 180 degrees. If it's trigonal planar, it's 120. If it's tetrahedral, it's 109.5 degrees. If it's trigonal bipyramidal, then we're going to have a separation of 90 degrees, and we're also going to have a separation of 120 degrees. So there's actually 2 bond angles that we're going to have for that one. And then octahedral will be a separation of 90. You have to know the bond angles. You have to know the electron domain geometries. And the other thing that's on, not the page that we looked at, the reference page that I gave you today, or that I made you look at today, but the other reference page that I gave you on Friday, and it says something about steric number. Steric number is the same thing as the number of electron domains. So if we have a steric number of 2, it means that I have 2 different bonds that are around the central atom. If I have a steric number of 3, it means that the central atom is bonded to 3 other atoms. Steric number of 4, it's bonded 4 times, so on and so forth. Okay, so now that we know these electron domain geometries, how do I predict shapes if not all of them are bonded? So again, my 5 categories of electron domain geometries. If I want to determine shape, this is what I have to do. We first have to start off, I'll give you something like this. I'll give you a compound, a molecule, and then you'll draw the Lewis structure first, because you draw your Lewis structure to determine how many bonding pairs do I have, and then how many non-bonding electron domains do I have. So if, for example, we did ammonia, NH3, I draw the Lewis structure, and so now I want to determine what is the electron domain geometry. Well, I have 3 bonding, 1 non-bonding, So because I have 4 electron domains, it's going to be in the tetrahedral electron domain geometry. But now what is its molecular geometry? That's the next question. So just because an electron domain geometry tells me how many bonding and how many non-bonding I have, the molecular geometry is what's going to actually define the positions of the atoms in the molecules. So electron domain doesn't always tell me shape, but it tells me how many electron domains I have. Molecular geometry tells me what are the actual positions of the atoms, okay? So that's the big difference between the two. And then again, Lewis structures, like we know, just tell me what is bonded to what in general and where electrons are. Doesn't tell me anything about shape, okay? So I'm going to give you a molecule or a compound. You'll go Lewis structure. Then you'll tell me how many electron domains there are and then tell me electron domain geometry. And then we'll go molecular geometry. But then you're going to go a step further and tell me steric number. You're going to tell me bond angles. And then we'll add later on, tomorrow and Wednesday, hybridization, and then whether it's polar or nonpolar. Okay, so in this case, because nitrogen has a lone pair, if I think about, it's in the tetrahedral category, but now I need to think about all of the subcategories in tetrahedral. 3 bonding and 1 non-bonding makes it trigonal pyramidal. So I like this table 9.2 in your book, because it goes through and says, here's the number of electron domains, and it breaks it up. Here's your electron domain geometry, and then here are all of the molecular geometry categories that are underneath those electron domain geometries, okay? If you would like a handout of this one too, I think that the other one that I gave you does the exact same thing. I just think this is spelled out really, really nicely. If you want me to copy this too, I can copy that. Just let me know, post on the blog, and I'll make a copy of that for tomorrow. So if I look at linear, there are no other little subcategories of linear. So ultimately, to be linear, it's 2 bonding domains and 0 non-bonding, and then so its molecular geometry is just linear. But if I look at trigonal planar, I look at the one that has 3 electron domains. If it has 3 electron domains, it's trigonal planar, and if it has 3 bonding and 0 non-bonding, it's still just trigonal planar. But if I have 2 bonding domains, so I have 2 bonds and 1 lone pair, then it's no longer trigonal planar. Its molecular geometry is called bent. If I move to tetrahedral, so here's 4 electron domains. If there's 4 bonding and 0 non-bonding, it stays tetrahedral. If there's 3 bonding and 1 non-bonding, so a total of 4 domains, but 3 are bonding and 1 is non-bonding, that's called trigonal pyramidal. And then if it's 2 and 2, that's also going to be bent. So let's note here, I go from no subcategories, so I just have what's linear is linear for its molecular geometry. And then trigonal planar, I could have 2 different categories here. Trigonal planar, it could stay trigonal planar or it could be bent. For tetrahedral, it could be 3 different options: tetrahedral, trigonal pyramidal, or bent. And all of these things are dictated, guys, by bonding domains and non-bonding domains. If I look to the 5th one, there are 4 different types that it could be. If I'm looking at them, 5 electron domains is trigonal bipyramidal. If I have 0 non-bonding and the rest are all bonded, it's trigonal bipyramidal, it stays the same. If there's 4 bonding, 1 non-bonding, it's called seesaw. If there's 3 bonding and 2 non, it's T-shaped. And if there's 2 and 3, it's linear. And then my very last one is octahedral, which is 6. 6 bonding, 0 non, stays octahedral. 5 and 1, it's called square pyramidal. And 4 and 2 is called square planar. So that's how this is going to break down. And they will ask you, this is the molecule, draw the Lewis structure. Once you draw the Lewis structure, predict the electron domain geometry. Once you have your electron domain geometry, predict the molecular geometry. Once you have the molecular geometry, tell me the bond angles. Okay. So this is saying the same thing. Within each electron domain, there might be more than 1 molecular geometry. So if I'm in the tetrahedral electron domain and I have a non-bonding pair here, it's no longer called tetrahedral, it's called trigonal pyramidal. And that's because, guys, the reason that we have these different ones too is because the bond angle is going to change a little bit. This atom here, between all of these atoms, is a 109.5 degree bond angle. But as soon as I take off that atom there, I'm left with this lone electron pair. And that lone pair of electrons is going to repel these atoms that it's attached to. So it's going to change the bond angle slightly because of that lone pair. So they're not the same thing, which is why I can't just call them all tetrahedral. Okay, so we already said about linear. If there's, also, if there are only two atoms in a molecule, so let's just say we have HCl, for example, then the molecule is going to be linear no matter what the electron domain is. So if there's two atoms in a molecule, then it's always linear, and there's no other exceptions to that. So an example here for linear, if I had two bonding domains, 0 non-bonding would be carbon dioxide. Trigonal planar, there's two molecular geometries, trigonal planar, and then bent. I'm going to kind of skip through these guys. Oh, never mind, just kidding. Okay, use the Vesper model to predict the molecular geometry of the following. So we have ozone, O3, we have SnCl3-, SeCl2, and then CO3 2-. So I'd like you to try these 4 for me, and then we'll look at those at the beginning of class before we do practice using Vesper and electron domains and bond angles. Okay, so let's go back and talk about the bond angle that we kind of alluded to on the one slide before. So this says non-bonding pairs are physically larger than bonding pairs. So a bonding pair of electrons, if I'm looking between these two here. So a bonding pair, if I'm looking at its electron density, is going to be roughly like this. It's associated, or it's in between two nuclei. Versus a non-bonding pair, its electron domain, the actual space that it occupies is just larger than a bonding electron pair. So because of this, I want us to look here at methane, CH4. So here I have 109.5 degree separation. That's what I see. Now, here we go. As soon as it loses that hydrogen here, I have a lone pair, and then I have 3 bonding. So for example, NH3, ammonia will do something like that. The bond angle really between it is 107 degrees. So for a trigonal pyramidal, it is not 109.5, it is 107 degrees. And I need to show that. I want to show that because this non-bonding pair is just actually physically larger than a bonding electron pair, it's going to minimize the bond angle between the atoms that I have bonded because this is so much more massive in space. So it's kind of pushing either of those sides down, okay? Guess what happens if now we're thinking about bent? Now I have 2 lone pairs with 2 bonding. So because I have these 2 really large non-bonding pairs, it should lower that degree of separation a little bit more, and it does. So I have 104.5 degree separation between the bonds now in comparison to 107, in comparison to 109.5. So we need to know that. As my non-bonding electron domains increase, the bond angles in the molecule are going to decrease. So a really good question that I would see on an FRQ would be to describe the bond angle in ammonia. And then they would want you to say that it would be less than 109.5 because non-bonding pairs are physically larger than